What makes the ocean so mysterious? At first glance, the ocean seems simple. Water, waves, salt. But look closer, and you'll find a world that defies easy answers. The ocean is Earth's last true frontier, more alien to us than many distant planets. We've mapped the surface of Mars in greater detail than our own seafloor. Beneath those rolling waves lies a landscape of mountains taller than Everest, trenches deeper than the sky is high, and ecosystems that thrive in complete darkness under crushing pressure. The mystery isn't just what lives down there, though that's part of it. It's also how little we understand about the ocean's role in our survival, how it breathes, how it remembers, how it connects every living thing on this blue planet. The ocean holds secrets written in brine and darkness, and we're only beginning to learn its language. Every expedition reveals something new, something impossible, something that makes scientists pause and reconsider what they thought they knew. How much of the ocean is still unexplored? Think about this for a moment. More than 80% of the ocean remains unmapped, unobserved, unseen by human eyes. We've sent people to the moon, rovers to Mars, probes beyond our solar system. Yet the majority of our own planet's ocean floor is a mystery. Most of what we know comes from sonar scans and remote vehicles, not direct observation. There are entire mountain ranges down there we've never visited, valleys that have never known light, creatures that have never been photographed or named. The deep ocean is vast beyond comprehension, covering over 70% of Earth's surface, with an average depth of about 12,000 feet. Exploring it isn't just difficult, it's extraordinarily expensive and technically challenging. Every dive is an engineering marvel. Every sample brought up is a gift. So when you think of explorers and pioneers, remember that some of the greatest frontiers aren't in space. They're right here, beneath the waves, waiting patiently in the dark. Where did all the ocean's water come from? Here's something surprising. Scientists aren't entirely certain where all this water came from. The ocean is so fundamental to our planet that we sometimes forget to ask how it got here in the first place. One leading theory suggests that during Earth's violent youth, countless comets and asteroids, essentially dirty snowballs from the outer solar system, bombarded our planet, delivering water molecule by molecule over millions of years. Another theory proposes that much of the water was here all along, trapped inside the rocky minerals that formed Earth, then released through volcanic outgassing as the planet's crust shifted and churned. Perhaps it was both, a cosmic collaboration between the stars and the stones. What we do know is that once the Earth cooled enough, water vapor condensed from the atmosphere and fell as rain. And it rained for thousands, perhaps millions of years, until the low places filled, until the ocean was born. That ancient rain still rolls in waves today. How deep is the deepest point on Earth? Let's go back in time to 1875, when a British ship called the HMS Challenger used weighted ropes to measure ocean depths. They found a place so deep it seemed impossible. We now call it the Challenger Deep, located in the Mariana Trench in the western Pacific Ocean. It plunges nearly 7 miles down, almost 36,000 feet below the surface. To put that in perspective, if you placed Mount Everest at the bottom, its peak would still be underwater by more than a mile. The pressure there is unimaginable, over 8 tons per square inch. That's like having 50 jumbo jets stacked on top of you. Only 3 people have ever descended to the bottom in person: Jacques Piccard and Don Walsh in 1960, and filmmaker James Cameron in 2012. What they found was not emptiness, but life, small, pale creatures moving through the silt. Even in the deepest, darkest, most inhospitable place on Earth, life finds a way. That realization is both humbling and strangely comforting. What happens to the human body in the deep sea? Imagine descending without protection into the deep ocean. What would happen? First, the cold. Deep water hovers just above freezing, and hypothermia would set in within minutes. But it's the pressure that poses the real danger. For every 33 feet you descend, the pressure increases by 1 atmosphere. At just 300 feet, your lungs would struggle. At 1,000 feet, the air in your body cavities would compress dramatically. Go deeper, and the physics becomes lethal. Your lungs would collapse. Nitrogen in your bloodstream would behave strangely, causing narcosis, a drunk-like state. Oxygen itself would become toxic under extreme pressure. Even your cells would begin to malfunction as proteins change shape under the strain. This is why deep-sea exploration requires specialized equipment, submersibles with thick hulls, or atmospheric diving suits that maintain normal pressure inside. The human body, for all its resilience, was not designed for the abyss. Yet our curiosity pushes us there anyway, protected by ingenuity and steel. How do ocean currents control our climate? Think of the ocean as a massive engine, constantly moving heat around the planet. Without ocean currents, Earth's climate would be unrecognizable. Warm water from the equator flows toward the poles, releasing heat into the atmosphere as it travels. Cold water sinks and flows back toward the equator, creating a global conveyor belt that takes roughly 1,000 years to complete one full circuit. This thermohaline circulation, driven by temperature and salinity differences, moderates temperatures worldwide. Europe, for instance, would be far colder without the Gulf Stream carrying tropical warmth northward. El Niño and La Niña patterns, driven by Pacific currents, affect weather across continents, bringing droughts or floods thousands of miles away. The ocean doesn't just respond to climate, it creates it. It remembers heat, stores carbon, and releases both slowly, dampening the extremes that would make life on land far more difficult. We live on a planet where the ocean is the thermostat, constantly adjusting, constantly balancing. Why are some oceans warm and others freezing cold? Here's a simple truth with complex consequences. Sunlight hits the equator more directly than the poles. That basic geometry creates everything else. Tropical oceans bask in consistent, intense sunlight year-round, warming the surface water to bath-like temperatures. But even in the tropics, descend below the sunlit zone, roughly 600 feet, and the temperature drops dramatically. There's a boundary called the thermocline, where warm surface water meets the deep cold, and it's like stepping from summer into winter in just a few dozen feet. Polar oceans, meanwhile, receive sunlight at a shallow angle, if at all, during winter months. Ice forms. Temperatures plummet below freezing for surface water, though it remains liquid thanks to salt. Yet even here, life thrives. Arctic cod, seals, whales, all adapted to the cold. Ocean temperature isn't uniform. It's layered, geographical, seasonal. It shapes where creatures live, where storms form, where coral grows. Temperature is the ocean's way of dividing itself into neighborhoods, each with its own character and residence. What lives at the bottom of the ocean? Descend to the seafloor in the deep ocean, and you enter a realm of strange beauty. There are fish with transparent heads and eyes that gaze upward, watching for prey silhouetted against the faint light from above. There are sea cucumbers that look like ambulatory sausages, vacuuming sediment for organic matter. Brittle stars with arms like delicate fractals, amphipods the size of dinner plates, eels with mouths full of needle teeth. Some creatures move slowly to conserve energy in this food-scarce environment. Others are surprisingly active, adapted to cold and pressure in ways we're still trying to understand. Many are scavengers, waiting for marine snow, the constant drift of dead material falling from the upper ocean, or the rare bonanza of a whale carcass that can sustain a community for years. The deep sea floor isn't empty desert. It's a living museum of evolutionary innovation, where every creature is a solution to problems we can barely imagine. And we've only glimpsed a fraction of what's down there. How do deep-sea creatures survive without sunlight? Let's pause on this mystery. Sunlight is the foundation of most life on Earth. Plants use it to make food through photosynthesis. And everything else eats plants, or eats something that ate plants. But sunlight penetrates seawater only so far, a few hundred feet in the clearest conditions, much less in murky water. Below that, permanent darkness. So how does anything survive? The answer is both simple and profound. They rely on what falls from above, and they rely on each other. Marine snow, tiny particles of dead plankton, fecal matter, bits of larger animals, drifts downward constantly. It's not much, but it's enough. Deep-sea creatures have evolved remarkable efficiency, slow metabolisms, and patience. Some can survive months without food. Others have evolved an alternative energy source, chemosynthesis, near hydrothermal vents. Bacteria convert chemicals like hydrogen sulfide into energy, forming the base of ecosystems that owe nothing to the sun. It's life finding another way, proving that the tree of existence has roots deeper than daylight. Do giant squids really exist? For centuries, sailors told stories of enormous squids rising from the depths, tentacles as thick as masts, eyes the size of dinner plates. Most dismissed these as myths, exaggerations born of too much rum and too many days at sea. But the sailors were right. Giant squids are real, and they're even stranger than the legend suggested. The largest confirmed specimens reach over 40 feet long, with eyes nearly a foot in diameter. The largest eyes in the animal kingdom, perfectly adapted to detect faint light and movement in the deep ocean twilight. For decades, scientists knew giant squids existed only from dead specimens washed ashore or found in the stomachs of sperm whales, their primary predator. No one had seen a living one in its natural habitat. Then, in 2004, Japanese researchers captured the first photographs. In 2012, video footage finally revealed these creatures in motion. Graceful, alien, utterly mesmerizing. They remain elusive, living in deep water, where they hunt fish and smaller squids. Somewhere in the ocean's depths, even larger ones might lurk, unseen and unrecorded. What is the largest animal in the ocean? It's not the giant squid, impressive as it is. The largest animal in the ocean, and the largest animal ever known to exist on Earth, surpassing even the biggest dinosaurs, is the blue whale. These magnificent creatures can reach lengths of over 100 feet and weigh as much as 200 tons. Their hearts alone are the size of small cars. Their tongues weigh as much as elephants. A small child could crawl through their largest blood vessels. Yet despite their enormous size, blue whales survive on some of the smallest creatures in the ocean. Krill, tiny shrimp-like animals barely bigger than your thumb. A blue whale can consume up to 4 tons of krill per day during feeding season, filtering them from the water through baleen plates. They're gentle giants, their haunting songs traveling hundreds of miles through the ocean, communicating across vast distances. To hear a blue whale sing is to hear the voice of the planet itself. Deep, resonant, ancient beyond measure. How do whales communicate across miles? Sound in water is a curious thing. It travels faster and farther than it does in air, about 4 times faster in fact. Whales have learned to use this to their advantage. Their songs, clicks, and calls can traverse entire ocean basins, reaching other whales hundreds or even thousands of miles away. Humpback whales sing complex songs that can last up to 20 minutes, repeated for hours. Males seem to be the primary singers, perhaps to attract mates or establish territory. The songs evolve over time, changing gradually within a population, like an underwater culture, passing down its music. Sperm whales use powerful clicks for echolocation, hunting giant squids in the darkness below. These clicks are among the loudest sounds produced by any animal, capable of stunning prey. Blue whales produce low-frequency pulses below the range of human hearing, infrasound that can circle the globe under the right conditions. The ocean is never silent. It hums with conversation. If only we have the tools to listen. Can sharks really smell blood from miles away? Here's a claim that's been repeated so often it's taken as fact. Sharks can smell a single drop of blood in an Olympic-sized swimming pool or detect blood from miles away. The truth is more nuanced, but still impressive. Sharks do have an extraordinary sense of smell. About 2/3 of their brain is devoted to olfaction, and they can detect certain amino acids at concentrations as low as 1 part per billion. But distance is tricky. In the open ocean, currents matter. Blood disperses and dilutes quickly. A shark might smell blood from a quarter mile away if the current carries it directly, but from miles away? Unlikely, unless conditions are perfect. What's more interesting is what sharks use their sense of smell for. They're not mindless eating machines, drawn to any blood. They're selective, curious, intelligent hunters that use multiple senses, smell, hearing, vision, electroreception, to navigate their world. They can detect the electrical fields generated by muscle contractions in prey. That's far more useful than smelling blood from miles away. Sharks are sophisticated creatures, refined by millions of years of evolution. Why are some fish bioluminescent? Imagine the deep ocean at night. It's already dark during the day. But at night, it's absolute. Or is it? Many deep-sea creatures produce their own light through a chemical reaction called bioluminescence. It's surprisingly common. Estimates suggest up to 90% of deep-sea animals have some form of bioluminescence. But why? Light serves many purposes down there. Some fish use it to attract prey, dangling glowing lures in front of their mouths like living fishing rods. Others use it for camouflage, a clever trick called counter-illumination. They emit light from their undersides that matches the faint light filtering from above, erasing their silhouette so predators looking up can't see them. Some use bioluminescent flashes to startle predators or communicate with potential mates. It's a language written in light, read by creatures who have never seen the sun. The chemicals involved are typically luciferin and an enzyme called luciferase, producing a cold light that wastes no energy as heat. Evolution's perfect flashlight in endless darkness. How do jellyfish live without a brain? At first glance, jellyfish seem impossibly simple. No brain, no bones, no heart, no blood. Just a gelatinous umbrella pulsing through the water, trailing tentacles behind. Yet they've survived for over 500 million years, outlasting countless more complex creatures. How? They possess something called a nerve net, a distributed network of neurons that allows them to sense and respond to their environment without centralized processing. They can detect light, chemicals, and touch. They can orient themselves. They can hunt and sting with remarkable precision. Each tentacle is lined with thousands of specialized cells called cnidocytes, containing nematocysts, tiny harpoons coiled under pressure. When triggered, they fire faster than almost any biological mechanism, injecting venom into prey or predators. Some jellyfish are practically immortal. The Turritopsis dohrnii, for instance, can revert to its juvenile polyp stage after reaching maturity, potentially cycling through life indefinitely. Simplicity, it turns out, is not weakness. It's elegant efficiency, refined over eons. Is there life around underwater volcanoes? Let's go to one of the most extreme environments on Earth, hydrothermal vents, where underwater volcanoes crack open the seafloor. Superheated water, sometimes exceeding 700 degrees Fahrenheit, erupts from these vents, carrying dissolved minerals that precipitate out, forming chimney-like structures. The water is acidic, toxic with hydrogen sulfide, devoid of oxygen. It sounds like a vision of hell. Yet here, improbably, ecosystems flourish. Giant tube worms grow up to 8 feet long, their bodies containing bacteria that convert the vent's chemicals into energy. Yeti crabs farm bacteria on their hairy claws. Vent shrimp, vent mussels, vent octopuses, all specialized for this hostile frontier. These ecosystems don't depend on sunlight. They run on Earth's internal heat, on chemistry alone. When scientists first discovered them in 1977, it revolutionized biology. If life could thrive here, what did that mean for other worlds? For icy moons orbiting Jupiter and Saturn, where liquid oceans might exist beneath frozen crusts. Hydrothermal vents opened our minds to life's possibilities. What happens at the Mid-Atlantic Ridge? The Mid-Atlantic Ridge is one of Earth's most dramatic features, though few people know it exists. It's a massive underwater mountain range running down the center of the Atlantic Ocean, from the Arctic to near Antarctica, over 10,000 miles long. This is where tectonic plates are pulling apart, where new oceanic crust is born. Magma rises from the mantle, cools, and solidifies, creating new seafloor in a process called seafloor spreading. The ridge is geologically active, punctuated by hydrothermal vents and volcanic activity. Iceland sits atop one of the few places where the ridge breaks the surface, which is why the island is so volcanically active. The ridge grows about an inch per year, roughly the rate your fingernails grow. That might not sound impressive, but over millions of years, it's enough to reshape continents, open oceans, and rewrite maps. The Mid-Atlantic Ridge is Earth's suture line, constantly opening, constantly healing, constantly creating. It's a reminder that our planet is alive, breathing, changing beneath the waves. Could an underwater earthquake cause a tsunami? Yes. Definitively, devastatingly, yes. Most tsunamis are born from earthquakes on the seafloor, particularly at subduction zones, where one tectonic plate slides beneath another. When a quake occurs, it can displace enormous volumes of water, sending waves radiating outward in all directions at speeds up to 500 miles per hour. In deep water, these waves are barely noticeable, maybe a foot high, passing ships without incident. But as they approach shallower coastal waters, something dramatic happens. The wave slows down and compresses, and all that energy has nowhere to go but up. The wave height increases, sometimes reaching over 100 feet. The 2004 Indian Ocean tsunami, triggered by a magnitude 9.1 earthquake, killed over 200,000 people across multiple countries. The 2011 Tohoku tsunami devastated Japan and caused the Fukushima nuclear disaster. These aren't just waves. They're walls of water, carrying unimaginable force, capable of traveling miles inland. The ocean reminds us, sometimes violently, that we live on a dynamic planet. How do coral reefs build entire ecosystems? Think of coral reefs as the cities of the sea. Dense, diverse, bustling with life. Yet the builders are tiny. Coral polyps, relatives of jellyfish, each no bigger than a pinhead. These polyps secrete calcium carbonate, building hard skeletons around themselves. Over time, layer upon layer, colony upon colony, these skeletons accumulate into massive reef structures. The Great Barrier Reef, visible from space, was built this way over thousands of years by countless billions of tiny animals. But corals aren't alone. They live in symbiosis with zooxanthellae, microscopic algae that live within their tissues. The algae photosynthesize, providing up to 90% of the coral's energy. In return, the coral provides the algae with protection and access to sunlight. This partnership is the foundation. Upon it, entire ecosystems arise. Fish find shelter in reef crevices. Sea turtles graze on algae. Sharks patrol the edges. Thousands of species, some found nowhere else on Earth, depend on these limestone cities. Reefs cover less than 1% of the ocean floor, but support about 25% of all marine species. Why are coral reefs dying? Here's something sobering. Coral reefs are in crisis. Rising ocean temperatures stress the corals, causing them to expel their symbiotic algae in a process called bleaching. Without the algae, corals lose their color and their primary food source. They can survive for a while, but if temperatures remain high, they starve. Prolonged bleaching events lead to widespread death. Ocean acidification, caused by increased carbon dioxide absorption, makes it harder for corals to build their calcium carbonate skeletons. Pollution, destructive fishing practices, and coastal development add further pressure. The Great Barrier Reef has experienced several mass bleaching events in recent years, losing vast areas of living coral. Reefs worldwide are declining at alarming rates. Scientists estimate that if current trends continue, most coral reefs could be gone by the end of this century. But there's also hope. Some corals show resilience. Restoration projects are underway, transplanting heat-tolerant species. Communities are establishing marine protected areas. The story isn't over, but it requires urgent action and collective will. Can the ocean heal itself from pollution? The ocean is vast, and it does have some capacity for self-renewal. Natural processes break down organic pollutants. Bacteria consume oil, and currents disperse contaminants. But there are limits. The ocean's ability to heal depends on the scale and type of pollution. Biodegradable materials eventually decompose, though it can take time. But plastics, they don't break down. They break apart into smaller and smaller pieces. Microplastics and nanoplastics that infiltrate every level of the marine food web. Heavy metals accumulate in sediments and living tissues. Chemical pollutants can persist for decades. When pollution exceeds the ocean's natural capacity to process it, ecosystems suffer. Dead zones, areas depleted of oxygen due to nutrient pollution, now exist in hundreds of coastal areas worldwide. The ocean isn't helpless, but neither is it invincible. It's absorbing the consequences of human activity at an unprecedented scale. Healing requires more than time. It requires us to stop adding more wounds, to protect what remains, and to actively restore what we've damaged. The ocean needs our help. How do microplastics affect marine life? Microplastics are everywhere in the ocean now. Tiny fragments smaller than 5 millimeters, invisible to the naked eye in many cases. They come from larger plastic debris breaking down, from microbeads in cosmetics, from synthetic fibers washing out of clothing. They float in surface waters, drift in the deep sea, embed themselves in Arctic ice and Pacific sediments. Marine creatures mistake them for food. Plankton ingest them. Fish eat the plankton. Larger predators eat those fish. Microplastics climb the food chain, accumulating in tissues. But the effects go beyond physical ingestion. Plastics carry toxic chemicals, both those used in manufacturing and those absorbed from surrounding seawater. These chemicals can disrupt hormones, affect reproduction, weaken immune systems. We're only beginning to understand the full impact. Studies have found microplastics in the bodies of fish sold for human consumption, in sea salt, in drinking water. The ocean and our own bodies are becoming repositories for our plastic waste. It's a problem that crosses boundaries, that connects every creature on this water planet. Is there really a garbage patch in the Pacific? Yes, though it's not what most people imagine. The Great Pacific Garbage Patch isn't a solid island of trash you could walk on. It's more like a diffuse soup of plastic particles and debris spread across an area roughly twice the size of Texas, held together by rotating ocean currents called the North Pacific Gyre. Much of it is microplastics and small fragments suspended in the water column or floating just below the surface. There are larger items too: fishing nets, bottles, containers. But the overall concentration varies. In some spots, you might scoop up water with visible plastic in every sample. In others, you'd see nothing from a boat. It's estimated to contain around 80,000 tons of plastic, though measuring accurately is difficult. And it's not the only garbage patch. Similar accumulations exist in other ocean gyres around the world. These patches are symptoms of a larger problem: our linear economy that produces, uses, and discards plastic without adequate systems for recovery or recycling. The ocean has become an unintended landfill. How much oxygen does the ocean produce? Here's something that might surprise you. Every second breath you take comes from the ocean. That's not poetic exaggeration. It's biochemistry. Phytoplankton, microscopic plant-like organisms drifting in the sunlit upper ocean, perform photosynthesis just like trees. They absorb carbon dioxide and release oxygen. Collectively, they produce about 50 to 80% of Earth's atmospheric oxygen, depending on the estimate. The most significant contributors are cyanobacteria, particularly a genus called Prochlorococcus, likely the most abundant photosynthetic organism on the planet. Trillions upon trillions of these microscopic cells, each invisible to the naked eye, working ceaselessly to oxygenate the atmosphere. They're the unsung heroes of planetary respiration, yet they're vulnerable. Ocean warming, acidification, and pollution all affect phytoplankton populations. When we talk about protecting the ocean, we're not just talking about saving whales or coral reefs. As important as those are, we're talking about preserving the living systems that make Earth habitable. The ocean breathes for us. It always has. What role does the ocean play in global warming? The ocean is Earth's climate buffer, absorbing over 90% of the excess heat trapped by greenhouse gases since the 1970s. Without this service, atmospheric temperatures would be dramatically higher. The ocean also absorbs about a quarter of the carbon dioxide we emit, helping to slow the pace of atmospheric warming. This sounds like good news, and in some ways it is. The ocean is buying us time, but there are costs. Warmer water holds less oxygen, stressing marine life. It expands, contributing to sea level rise. It fuels stronger hurricanes and alters weather patterns. Absorbed carbon dioxide forms carbonic acid, making seawater more acidic. Ocean acidification, which threatens calcifying organisms like corals, shellfish, and some plankton. The ocean is taking on our burden, but it's changing in the process. Ice is melting, currents are shifting, ecosystems are struggling. The buffer has limits. The ocean can't keep absorbing indefinitely without consequences that will eventually affect us all. It's already happening. The question is how we respond. Could the ocean swallow cities? Sea levels are rising, and that's not a distant future scenario. It's happening now. Thermal expansion of warming water and melting ice sheets both contribute. The rate is accelerating. Over the 20th century, seas rose about 7 inches. By 2100, estimates range from 1 to 4 feet of additional rise, depending on how quickly ice melts and how much we reduce emissions. That might not sound like much, but even a foot can be devastating. Many major cities, New York, Miami, Shanghai, Mumbai, Lagos, Jakarta, sit just above current sea level. Storm surges ride higher on elevated seas. High tides flood streets more frequently. Coastal infrastructure becomes vulnerable. Some island nations face existential threats. The Maldives, Marshall Islands, Tuvalu, entire cultures could be displaced. We're already seeing it. Miami Beach floods during high tides. Venice is sinking. Bangladesh loses coastal land to erosion. The ocean isn't intentionally swallowing cities. It's simply responding to physics, reclaiming space as it warms and grows. Whether cities survive depends on adaptation, engineering, and most importantly, whether we slow the warming. How do icebergs form and drift? Let's travel to the ends of the Earth, where ice sheets and glaciers meet the sea. Over millennia, snow accumulates on land, compressing into ice. Gravity pulls the ice downward and outward, forming slow-moving rivers of ice, glaciers. When these glaciers reach the ocean, the ice extends over the water, forming floating ice shelves. Eventually, chunks break off in a process called calving. These are icebergs. The crack of a calving glacier is like thunder, and the splash can generate waves that travel for miles. Icebergs drift with currents and winds, melting slowly as they encounter warmer water. Most of an iceberg's mass sits below the surface, hence the phrase tip of the iceberg. The ratio varies, but typically about 90% is underwater. Icebergs come in all sizes, from small chunks called growlers to massive tabular bergs, the size of small countries. They're time capsules, holding ancient air bubbles and secrets about past climates. And as the planet warms, more are calving, more frequently, in larger pieces. What lies beneath the Arctic ice? The Arctic Ocean, covered by a shifting cap of sea ice, has long been one of Earth's least explored regions. Harsh conditions, extreme cold, and months of darkness made it nearly inaccessible. But beneath that ice lies a surprisingly active world. The seafloor features abyssal plains, mountain ranges, and the Gackle Ridge, a mid-ocean spreading center where volcanic activity occurs even under ice. There are deep basins holding cold, dense water. Recently, scientists have discovered life thriving here in unexpected abundance. Algae grow on the underside of ice. Fish and crustaceans navigate the frigid water. Polar bears, seals, and walruses depend on the ice as platforms for hunting and rest. And there are resources, oil, gas, minerals, leading to increased human interest now that climate change is making the region more accessible. But accessibility brings risk. The Arctic is changing faster than almost anywhere on Earth. Ice is retreating, ecosystems are shifting, and what lies beneath is becoming vulnerable to exploitation and disruption before we even fully understand it. Can we find hidden continents underwater? In 2017, scientists announced something remarkable: the discovery of Zealandia, a largely submerged continent in the southwestern Pacific Ocean. It's about two-thirds the size of Australia, but 94% of it lies underwater. New Zealand and New Caledonia are its visible peaks. The discovery wasn't sudden. Geologists had suspected for decades that the region's geology was distinct, but it took modern satellite data and seafloor mapping to confirm that Zealandia meets the criteria for a continent: a distinct landmass with defined geological boundaries, unique crust, and elevation compared to the surrounding oceanic crust. This raises intriguing questions. Are there other hidden continents? Possibly. Much of Earth's seafloor remains poorly mapped. There could be submerged microcontinents, fragments left over from ancient supercontinents like Gondwana and Pangaea, now hidden beneath waves. Each discovery reshapes our understanding of Earth's structure and history. The continents we see today are just the parts that happen to stick above sea level. The full story is written beneath the ocean. What secrets does the Mariana Trench hold? The Mariana Trench, Earth's deepest place, has been visited by humans only a handful of times. What have we found? More than emptiness and pressure. There's life, of course. Amphipods, snailfish, strange creatures adapted to crushing conditions, but also evidence of humanity's reach. In 2019, a submersible discovered a plastic bag and candy wrappers at the bottom of the trench. Our pollution has reached even the most remote places on Earth, but the trench holds other secrets too. Unique microbial ecosystems, unusual geological features, possibly undiscovered species. Each dive reveals something new. The trench also plays a role in Earth's geology. It's a subduction zone where the Pacific plate is being pulled beneath the Mariana plate, sinking back into the mantle. Water carried down with the descending plate can trigger volcanic activity, contributing to the Ring of Fire. The trench is a window into Earth's interior processes, a laboratory for extremophile biology, and a humbling reminder that even our deepest explorations barely scratch the surface. Are there underwater rivers? At first, this sounds impossible. A river underwater? But they exist, and they're mesmerizing. When seawater with different densities, due to differences in temperature or salinity, meet, the denser water can flow beneath the lighter water, creating currents that behave remarkably like rivers. The most famous example is in the Black Sea, where an underwater river of saltier, denser water flows along the seafloor through a channel, complete with banks and even floodplains. If this river were on land, it would be one of the world's largest. Similar phenomena occur elsewhere. In cenotes, underwater caves in Mexico, freshwater and saltwater layers create eerie interfaces. Divers can literally swim through the boundary between them, watching it shimmer like a mirage. There are also brine pools in the deep ocean, where hypersaline water accumulates in seafloor depressions, creating underwater lakes with distinct shorelines. They're toxic to most marine life, but harbor specialized bacteria. These hidden rivers and lakes remind us that the ocean isn't uniform. It has layers, boundaries, hidden structure. How does the ocean glow at night? On certain nights, in certain places, the ocean comes alive with light. Bioluminescent plankton, dinoflagellates, tiny single-celled organisms, create this magic. When disturbed by movement, they emit flashes of blue-green light. A wave breaking on shore sparkles. A boat's wake leaves a glowing trail. You run your hand through the water and it lights up like stardust. The effect is called bioluminescent bays, or glowing seas. And some locations are famous for it. Mosquito Bay in Puerto Rico, Luminous Lagoon in Jamaica, beaches in the Maldives. But the phenomenon can occur almost anywhere when conditions are right. Warm water, calm nights, and dense concentrations of the right plankton species. Why do they glow? Possibly as a defense mechanism. The flash might startle predators, or attract larger predators to eat whatever disturbed the plankton. It's a living burglar alarm. Standing in glowing water, watching your footsteps illuminate the sand. It's easy to forget the biology and just feel wonder. The ocean has always had this magic. We've simply learned to recognize it. What are rogue waves, and how do they form? For centuries, sailors told stories of enormous waves appearing without warning, walls of water rising far higher than the surrounding seas, capable of smashing ships and disappearing as suddenly as they appeared. Scientists dismissed these as myths or exaggerations. Until 1995, when an oil platform in the North Sea recorded a wave 90 feet tall, nearly twice the height of the surrounding waves. It was undeniable proof that rogue waves exist. We now know they're more common than once thought, though still rare and unpredictable. They can form through several mechanisms. Sometimes waves traveling in different directions converge, their energies combining into one massive peak. Sometimes ocean currents focusing wave energy, or underwater topography can amplify waves dramatically. Wind patterns and storm systems can also play a role. Rogue waves are dangerous, precisely because they're anomalies. Ships are designed to handle typical wave heights for a given sea state. A rogue wave exceeds those parameters, striking with enormous force. Modern satellite observations have detected thousands of potential rogue waves, helping scientists understand their patterns. But predicting exactly when and where one will form remains extremely difficult. The ocean still holds surprises. Could a mega tsunami really happen? The answer is yes, though perhaps not in the way disaster movies portray. Most tsunamis are triggered by underwater earthquakes, but there are other mechanisms that could produce truly catastrophic waves. One scenario involves massive landslides. If a significant portion of a volcanic island's flank collapsed into the ocean, say from Cumbre Vieja in the Canary Islands or from a Hawaiian volcano, it could displace enormous volumes of water, potentially creating waves hundreds of feet high. Geological evidence shows these events have occurred in Earth's past, 8,000 years ago. A submarine landslide off Norway created the Storegga Slide tsunami, which reached heights of 80 feet and affected coastlines around the North Sea. Another scenario involves asteroid impacts. A large asteroid striking the ocean could generate waves of unimaginable scale. The good news is that these mega events are extraordinarily rare, occurring on timescales of thousands or tens of thousands of years. The concern is that coastal populations are far larger now than in the past. A mega tsunami today would affect millions. How do submarines explore the deep ocean? Human bodies can't withstand deep ocean pressure, so we've built machines to go where we cannot. Research submersibles are marvels of engineering. Pressure hulls made of titanium or specialized alloys designed to maintain normal atmospheric pressure inside, while outside forces would instantly crush unprotected structures. The famous DSV Alvin has been exploring the deep since 1964, discovering hydrothermal vents and investigating the Titanic wreck. Newer submersibles like the Limiting Factor have reached the deepest points in all 5 oceans. These craft typically carry 2 or 3 people in cramped quarters, with thick viewports offering limited visibility. They descend slowly, sometimes taking hours to reach the bottom, where they can spend a few hours exploring before ascending. Remotely operated vehicles, ROVs, tethered to ships allow exploration without risking human life. Autonomous underwater vehicles, AUVs, can be programmed to survey vast areas independently. Each technology has strengths, but all share a common challenge. The ocean is vast, and each expedition covers only a tiny area. What tools do scientists use underwater? Beyond submersibles, ocean scientists deploy an impressive array of tools. Sonar, sound navigation and ranging, maps the seafloor by bouncing sound waves off the bottom and measuring return times. Multi-beam sonar creates detailed 3-dimensional maps. Seismometers on the ocean floor detect earthquakes and study Earth's interior structure. CTD sensors measure conductivity, temperature, and depth, revealing ocean structure. Water samplers called Niskin bottles capture water from specific depths for chemical analysis. Plankton nets, coring devices that extract sediment samples, underwater cameras, acoustic recorders that capture whale songs and other sounds. The toolkit is diverse. Recently, environmental DNA sampling has revolutionized marine biology. By filtering seawater and analyzing the DNA it contains, scientists can identify species present without seeing them directly. Satellite remote sensing monitors ocean temperature, color, indicating phytoplankton abundance, wave heights, and ice extent. Ocean gliders, drifters, and Argo floats, thousands of autonomous instruments dispersed across the global ocean, continuously collect data, transmitting it via satellite. We've never had better tools, but the ocean remains vast beyond our capacity to monitor fully. What sounds can we hear from the ocean's depths? The ocean is not silent. Drop a hydrophone, an underwater microphone, into the sea, and you'll hear a symphony. Whales singing, dolphins clicking, fish grunting, croaking, drumming, shrimp snapping, a sound so pervasive it creates a constant crackling background noise in many coastal areas. Icebergs calving with thunderous cracks, underwater volcanoes rumbling, earthquakes generating low-frequency booms that travel across ocean basins. Rain pattering on the surface creates a distinct sound. Wind and waves contribute. Human-made sounds are there too. Ship engines, sonar, pile driving, seismic surveys, forming an increasingly loud component of the ocean's acoustic environment. Sound is crucial for marine life. Many species rely on it more than sight. This is why noise pollution is such a concern. Loud sounds can interfere with whale communication, disorient dolphins, stress fish. In 1997, underwater microphones detected an extremely loud, ultra-low frequency sound that traveled over 5,000 kilometers, called the bloop. It was likely created by an icequake. ice fracturing and calving from Antarctic glaciers. But for years, the mystery captivated imaginations. Are there lost civilizations beneath the sea? The ocean has swallowed countless human settlements over millennia. Rising seas at the end of the last ice age flooded vast coastal areas where people lived. Earthquakes and tsunamis have claimed cities. Erosion has taken others. We've found submerged ruins in many locations. Off the coast of Egypt, the ancient cities of Heraklion and Canopus lay underwater for over 1,000 years before archaeologists discovered them. In the Mediterranean, dozens of submerged sites reveal ancient harbors, buildings, shipwrecks. In India, the Gulf of Kambat has yielded structures some claim are 9,000 years old. Though this remains controversial, near Japan, the Yonaguni Monument, a rock formation with seemingly artificial features, sparks debate about whether it's natural or man-made. Most underwater archaeological sites aren't lost civilizations in the Atlantis sense. Advanced societies vanished without trace. They're coastal settlements gradually overcome by rising seas or sudden disasters. Still, there's something haunting about exploring a drowned city, swimming through streets that once bustled with life, now home only to fish and silence. Could Atlantis have been real? Plato wrote about Atlantis around 360 BCE, a powerful island civilization that supposedly sank into the ocean in a single day and night of catastrophe. For over 2,000 years, people have debated whether it was real or allegorical. Most scholars believe Plato invented Atlantis as a philosophical device, a cautionary tale about hubris and power, but some think it might have been inspired by real events. The Minoan civilization on Crete and the island of Thera, modern Santorini, experienced catastrophic volcanic eruptions around 1600 BCE, with Thera's explosion being one of the largest in recorded history. It destroyed settlements, generated tsunamis, and may have contributed to the Minoan civilization's decline. Perhaps stories of this disaster, passed down and embellished, influence Plato's narrative. Other theories place Atlantis everywhere from the Mediterranean to Antarctica. The truth? We'll probably never know for certain. No definitive evidence of Atlantis has ever been found. But the story endures because it touches something deep. Our awareness that the ocean has taken much from us and might hold secrets we've forgotten. How do animals navigate vast oceans? Sea turtles hatch on beaches, scurry to the ocean, and spend years wandering thousands of miles through open water. Then decades later, they return to the exact same beach where they were born to lay their own eggs. How? Salmon do something similar, swimming from rivers to ocean and back again to their natal streams. Seabirds forage over featureless expanses of water and find their way home to tiny islands. The mechanisms are varied and remarkable. Many marine animals use Earth's magnetic field as a compass, detecting subtle variations that create a mental map. Sea turtles may imprint on their birth beach's magnetic signature. Some species use the sun's position, adjusting for time of day, celestial navigation. Others use olfactory cues, following chemical gradients in the water. Seabirds may use visual landmarks, wind patterns, even the stars at night. Recent research suggests some animals detect polarized light, infrasound, or pressure changes. It's likely most species use multiple cues, cross-referencing information to navigate accurately. These abilities, refined over millions of years, put our human sense of direction to shame. Why do sea turtles return to the same beach? This behavior, called natal homing, is one of nature's great mysteries. Female sea turtles travel thousands of miles across open ocean, then swim directly to the beach where they hatched, sometimes decades earlier. The leading theory involves geomagnetic imprinting. When turtles hatch and enter the ocean, they may memorize the unique magnetic signature of their natal beach. Earth's magnetic field varies slightly from place to place, creating a kind of magnetic map. How do dolphins use echolocation? Dolphins are masters of biological sonar. They produce clicks, rapid pulses of sound, that travel through the water and bounce off objects. By analyzing the returning echoes, dolphins can determine an object's size, shape, distance, speed, even internal structure. A dolphin can distinguish between different species of fish, detect a coin-sized object hundreds of feet away, and identify whether something is made of metal, plastic, or flesh. The clicks originate in air sacs near the blowhole and are focused into a beam by the melon, an oil-filled organ in the dolphin's forehead. Returning echoes are received through the lower jaw and transmitted to the inner ear. The dolphin's brain processes this information incredibly quickly, building a detailed acoustic picture of its surroundings. This is crucial in murky water or darkness where vision is limited. Echolocation allows dolphins to hunt, navigate, and communicate. It's so sophisticated that the military has studied dolphins for mine detection. Some researchers believe dolphins can use intense sound bursts to stun prey. It's a superpower we're only beginning to understand. Do fish sleep? This seems like a simple question, but defining sleep underwater is tricky. Fish don't have eyelids, so they can't close their eyes. They don't have the same brain structures mammals use for sleep. Yet most fish exhibit rest periods, times when they're less active, less responsive, with reduced metabolism. Some fish hover in place. Others settle on the bottom or wedge themselves into crevices. Parrotfish secrete a mucus cocoon around themselves at night, possibly to mask their scent from predators. Sharks, who need to keep moving to breathe, show reduced activity patterns that might constitute sleep. Recent research suggests fish do experience something analogous to sleep. Zebrafish, for example, show sleep-like states, and when deprived of rest, they exhibit rebound sleep, sleeping longer to compensate, just like mammals do. The evolutionary origins of sleep remain mysterious, but it appears to be fundamental to animal life, whether in air or water. Fish sleep differently than we do, but they do rest. Even the ocean needs to close its eyes sometimes, in its own way. How does pressure affect life in the deep? At the ocean's surface, atmospheric pressure is about 14 pounds per square inch. Descend to 33 feet, and it doubles. At 3,000 feet, it's about 90 times surface pressure. At the Mariana Trench's bottom, it's over 16,000 pounds per square inch, more than 1,000 times surface pressure. How does anything survive? Deep-sea creatures have evolved remarkable adaptations. Their bodies contain no air spaces that would collapse, no swim bladders, no air-filled cavities. Their cells use special molecules, particularly trimethylamine N oxide, that stabilize proteins under pressure. Their membranes contain unique lipids that remain flexible in cold, high-pressure environments. Some fish, like snailfish found at over 26,000 feet, look gelatinous and fragile, but that structure actually helps them survive. They're not fighting the pressure, they're built to live in equilibrium with it. Bring a deep-sea creature rapidly to the surface, and the sudden pressure drop can be fatal, causing dissolved gases to expand and tissues to rupture. Pressure shapes life as profoundly as temperature or chemistry. Could humans ever live underwater? For centuries, humans have dreamed of underwater habitats. We've experimented with the idea. Jacques Cousteau's Conshelf stations in the 1960s housed aquanauts underwater for weeks. The U.S. Navy's Sea Lab program did similar research. Aquarius, an underwater research station off the coast of Florida, still operates today, hosting scientists who live submerged for days or weeks, studying marine life and testing technologies. These habitats typically sit in relatively shallow water, around 60 feet, where divers can still exit relatively safely. Living deeper would require more complex engineering. The challenges are immense. Pressure must be managed, air must be supplied, waste must be removed, food must be brought in. Psychological effects of confinement in a small space, surrounded by an alien environment, are significant, and the cost is enormous. Currently, it's cheaper and easier to commute from the surface. But technology improves. Perhaps future underwater cities will exist. Research stations, mining operations, even tourism destinations. The ocean is vast and largely unused. Whether we should live there is a different question than whether we could. What would happen if the oceans disappeared? Imagine, impossibly, that all ocean water vanished. What would remain? First, topography we've never seen. The hidden 70% of Earth's surface. Vast abyssal plains, mountain ranges higher than the Himalayas, trenches deeper than any canyon, the mid-Atlantic ridge exposed, Iceland connected to this serpentine mountain chain, continental shelves, gently sloping underwater extensions of continents, suddenly transformed into coastal plains. But the consequences would be catastrophic. Ocean currents drive weather patterns. Without them, temperature extremes would intensify. Coastal areas would experience wild swings between scorching days and freezing nights. The ocean produces much of our oxygen. Without phytoplankton, atmospheric oxygen would gradually decline. Carbon dioxide would build up faster. The water cycle would collapse. No evaporation from ocean surfaces means dramatically reduced rainfall. Deserts would expand. Ecosystems would fail. Marine life would die, obviously. But terrestrial ecosystems depend on oceans too. For climate regulation, nutrient cycling, moisture, Earth would become unrecognizable, uninhabitable. We live on a water planet. Remove the water, and it's no longer home. How will rising sea levels change our future? Sea level rise isn't a single event. It's a gradual transformation already underway. Even if we stopped all emissions today, seas would continue rising for decades or centuries due to thermal inertia and ice sheet dynamics. The question isn't whether seas will rise, but how much and how fast. Current projections suggest 1 to 4 feet by 2100, possibly more if ice sheets collapse faster than expected. This will reshape coastlines worldwide. Low-lying regions will experience increased flooding. Some areas will become permanently submerged. Salt water will intrude into freshwater aquifers, contaminating drinking water supplies. Agriculture in coastal areas will suffer. Infrastructure, roads, power plants, airports built near coasts will require expensive protection or abandonment. Millions of people will be displaced, creating climate refugees. Wealthy nations may build seawalls and pump systems, like the Netherlands has for centuries. Poorer nations may lack resources to adapt. The social, economic, and political consequences will be profound. But rising seas also present opportunities to reimagine coastal cities, to develop new technologies, to build more sustainably. The future is being written now in the choices we make. Could the ocean hold the key to new medicines? Marine organisms have evolved in an environment dramatically different from land, and they've developed unique biochemistry to survive. Many produce compounds we've never seen before, molecules that defend against predators, prevent fouling, enable survival under extreme conditions. These compounds are incredibly promising for medicine. Cone snails, for instance, produce venom containing conotoxins, peptides that block specific nerve signals. One conotoxin has been developed into a powerful painkiller for chronic pain. Sponges have yielded anti-cancer compounds. Algae produce substances with antiviral and antibacterial properties. Horseshoe crab blood contains a substance called LAL, used to test for bacterial contamination in medical equipment and vaccines. Marine bacteria from hydrothermal vents produce enzymes used in biotechnology. We've barely scratched the surface. With millions of marine species, most unstudied, the ocean represents a vast pharmaceutical library. But there's urgency. Species are going extinct before we can study them. Habitats are degraded. The medicine that could cure tomorrow's diseases might vanish today. Protecting ocean biodiversity isn't just about conservation, it's about preserving potential futures. What does the future of the ocean look like? The honest answer is uncertain. Two futures are possible. In one, we continue on our current path. Temperatures rise, ice melts, oceans acidify, coral reefs largely disappear. Fish populations collapse from overfishing and habitat loss. Plastics accumulate. Dead zones expand. The ocean becomes less productive, less diverse, less resilient. Coastal communities face increasing disasters. The consequences ripple through every ecosystem, including our own. In the other future, we change course. We rapidly reduce emissions, slowing warming. We establish vast marine protected areas, allowing ecosystems to recover. We develop sustainable fishing practices. We clean up pollution and prevent new contamination. We invest in restoration, replanting mangroves, transplanting corals, removing invasive species. Technology helps. Renewable energy, better materials, improved monitoring. In this future, the ocean stabilizes, adapts, endures. Life continues its ancient dance. Which future occurs depends on choices made in the next few decades. The ocean's future is our future. They're inseparable, and there's still time to choose hope over resignation. Action over despair. Why should we protect the blue planet? Perhaps the better question is, how could we not? The ocean is Earth's life support system. It regulates climate, produces oxygen, feeds billions of people, cycles nutrients, and hosts the majority of life on our planet. It shaped our evolution. Life began in the ocean billions of years ago. It shapes our culture. Nearly half of humanity lives within 100 miles of a coast. The ocean is in our blood. Literally, our cells contain salt concentrations similar to ancient seawater, a reminder of our origin. But beyond practical reasons, there's something deeper. The ocean inspires wonder. It reminds us we're part of something larger than ourselves. Standing at the shore, watching waves roll in from distant storms, you're connected to the whole planet, to the fish swimming below, to the plankton drifting in currents, to the water evaporating to form clouds. The ocean doesn't need us. We need it. Protecting the ocean is protecting ourselves, our children, our future. And perhaps, in learning to care for the ocean, we learn to care for each other, to think in longer time frames, to act with humility and wisdom. The blue planet is all we have. Let's treat it like home. Marine organisms have evolved in an environment dramatically different from land, and they've developed unique biochemistry to survive. Many produce compounds we've never seen before, molecules that defend against predators, prevent fouling, enable survival under extreme conditions. These compounds are incredibly promising for medicine. Cone snails, for instance, produce venom containing conotoxins, peptides that block specific nerve signals. One conotoxin has been developed into a powerful painkiller for chronic pain. Sponges have yielded anti-cancer compounds. Algae produce substances with antiviral and antibacterial properties. Horseshoe crab blood contains a substance called LAL, used to test for bacterial contamination in medical equipment and vaccines. Marine bacteria from hydrothermal vents produce enzymes used in biotechnology. We've barely scratched the surface. With millions of marine species, most unstudied, the ocean represents a vast pharmaceutical library. But there's urgency. Species are going extinct before we can study them. Habitats are degraded. The medicine that could cure tomorrow's diseases might vanish today. Protecting ocean biodiversity isn't just about conservation. It's about preserving potential futures. What does the future of the ocean look like? The honest answer is uncertain. Two futures are possible. In one, we continue on our current path. Temperatures rise, ice melts, oceans acidify, coral reefs largely disappear, fish populations collapse from overfishing and habitat loss, plastics accumulate, dead zones expand, the ocean becomes less productive, less diverse, less resilient. Coastal communities face increasing disasters. The consequences ripple through every ecosystem, including our own. In the other future, we change course. We rapidly reduce emissions, slowing warming. We establish vast marine protected areas, allowing ecosystems to recover. We develop sustainable fishing practices. We clean up pollution and prevent new contamination. We invest in restoration, replanting mangroves, transplanting corals, removing invasive species. Technology helps, renewable energy, better materials, improved monitoring. In this future, the ocean stabilizes, adapts, endures. Life continues its ancient dance. Which future occurs depends on choices made in the next few decades. The ocean's future is our future. They're inseparable, and there's still time to choose hope over resignation, action over despair. Why should we protect the blue planet? Perhaps the better question is, how could we not? The ocean is Earth's life support system. It regulates climate, produces oxygen, feeds billions of people, cycles nutrients, and hosts the majority of life on our planet. It shaped our evolution. Life began in the ocean billions of years ago. It shapes our culture. Nearly half of humanity lives within 100 miles of a coast. The ocean is in our blood. Literally, our cells contain salt concentrations similar to ancient seawater, a reminder of our origin. But beyond practical reasons, there's something deeper. The ocean inspires wonder. It reminds us we're part of something larger than ourselves. Standing at the shore, watching waves roll in from distant storms, you're connected to the whole planet, to the fish swimming below, to the plankton drifting in currents, to the water evaporating to form clouds. The ocean doesn't need us. We need it. Protecting the ocean is protecting ourselves, our children, our future. And perhaps, in learning to care for the ocean, we learn to care for each other, to think in longer time frames, to act with humility and wisdom. The blue planet is all we have. Let's treat it like home,